Hello class, welcome to another topic of memory management, chapter 4, which is the non-contiguous allocation. It says that non-contiguous allocation is the size of the logical address, no, which is generated by the CPU is greater than or equal to the size of the physical address space, which is then generated by the main memory. So that there will be an efficient of use of multi-programming since this is particular to the operating systems and also can run larger programs in small memory area. So as you can see in the figure, this is an example of how we can illustrate the non-contiguous allocation. So there would be 2 to the n, which is n indicates that the bits required for the logical address. And this will tells us the process size. And also this would be greater than or equal to 2 to the m, which is indicates the physical address space, which is part of the main memory that is allocated to the process. So usually n is greater than m, and process size is greater than given memory area. So there is a need of mapping in terms of the logical address space to the physical address space, which is this will be done by the use of the MMU, Memory Management Unit. So in part of non-contiguous allocation, there would be solution or implementation that we'll be using in non-contiguous allocation. So when we say non-contiguous allocation, that certain process is allocated in a memory in different area they are allocated. Unlike with the contiguous, there are a series of how they are allocated in a memory. So in non-contiguous, bisan asa siya nga area of the memory can be allocated. So from this, we have several algorithms that we'll be using in non-contiguous. We have paging and segmentation. So first, let's have the paging. So in terms of paging, memory management technique, that permits the physical address space of a process to be non-contiguous. So physical memory is divided into blocks of the same size called frames. So in physical memory, there are called frames with the same size of blocks. Kung 1 KB na siya, so 1 KB to tanan ang allocated for that. So logical memory is divided into blocks of the same size called pages. So in terms of physical memory, we have frames. So in terms of logical address spacing or logical memory, we have pages. With also regards to the same size nga allocation. So a frame can have the same size as a page, must have a same size with a page. And is a place where a logical page can be physically placed. A process need to locate, generated by this logical address space, kailangan na to siya i-locate dito sa atong main memory, which is from the physical memory address space. Para malocate na to asa to nga certain frame or code, na kailangan to execute. So we need to point out asa dapat sika ni siya nga logical address space na belong to a physical address space. Ana siya pag i-translate niya using the paging. So this is some of the illustration of how paging occurs, like if we have a process, so they are divided in different pages, in the same size of blocks. And we have here a main memory, which also divided in frames. So kung ato na siyang gamitan og paging, so in non-contiguous allocation, so these different blocks from pages allocate siya into the memory, in which is napod din na ang frames. So as you can see, the blue blocks represented by pages, so can be allocated in a frames, with the same size also. So We have a page model which is address translation yung gaka-occur during sa paging, no. Example, if we have a main memory which is a block, contains a blocks also of pages. So we have page 0, 1, 2, and 3. So inside the page 0, there will be several instructions, no, allocated. We have 0, 2, 3, which also have data entry. So this is called pages kaning mga blocks. And also here in a physical memory, we have blocks also, which is called frames. So from that, no, we can create a page table from this scenario. So in page 0, we can says that we can locate that one in a frame 1, no? Since diha siya na belong, diha siya na gibutang, no, in terms of physical memory. So page 1 will have the allocation on frame 4, and page 2 will have it on page 3, frame 3, and page 3 will have frame 7. So ang mahitabo sa address translation is that mag-allocate sample of the page, no, will allocate 4 bits. So this indication na kaning block here nga kaning block dinhi na bit, no, like 00 mo nang mag-indicate sa imong page number. So the red one will indicate the what instruction, specific instruction na kung ipangitaon dito, no. So sample, if we have a line of code na 00, so this would be a line of code of 0, no, kani siya nga area 0A. So if we need to locate 01, so we need to specify 01 nga line of instruction. So 2 mo po na siyang designation niya. So the first 2 bits would be your indications at page number, and the other would be the offset, no? Kung asa na specific nga instruction na to ang i-fetch. So muna na siya na natay page table, and also unsay gabuhaton ani niya sample if we will go to page 2, no, like page 2 with instruction 8i, no. So atong ibutang din we have 1000. So the black bits na 2 bits would indicate page 2. So pag abot sa to sa framing sa page table, natay page table, so mo ni siya naagitan nakabalutang page 2 to siya using the block bits. Dayon naka-frame dayon siya sa as indicated the page table, naka-indicate siya na naa siya sa frame 3, which is your indication also nga ang imuhang offset dinhi sa page kay 00, no, kaning 8i 00 offset niya. So pag check niya diri, this is frame 3, so mo ni hang code, no, na binary ni frame 3 which is 3 bit. So kung para makuha na to ang 8i, we need to add the following bits, no, like kaning 001 for frame indication, and the remaining offset from page, no, like 00, so that we can able to say nga malocate na to ning 8i here sa frame 3, no. Mo ingana yung pag-translate from your main memory to your physical memory. So this is the hardware setup of your paging. So we have CPU will generate logical address, which is generated also by paging and an offset. And it will get through the page table and locate asa dapit nga frame siya na belong. So after locating the frame, no, so physical address, use that to locate that in the physical memory. So frame plus the offset also. So makita na nato asa to siya na locate tong yang gi-translate nga address. So page table, remember this guys, like each process has its own page table stored in a memory. So page table is organized a series of entries. So the number of entries in a page table is equal to the number of pages of logical address space. So page table contains frames, no? Page table contain frames, as you can see in the figure last kanina. And to make usage more efficient, the page table is kept in the main memory, and page table base register PBTR points to the page table. So in page table implementation, we have to maintain 4 bits per page table entry with the use of bits, the use bit, the modified bit, the valid bit, and read-only bit. So this is the advantages of paging. So no external fragmentation, since also we discussed that one late the other part no of memory management na sa tong external fragmentation. No, we can't use even though that certain process is nahuman na siya or terminated na yung process. So we can't use that memory allocation because of the external fragmentation. So simple memory management algorithm is used in paging. No, and swapping is very easy implementation in paging. So disadvantages, it can reduce the internal fragmentation but never nga mawala ang internal fragmentation in paging. So page table may cost memory, since then we will, if we upgrade no the size of the page table also, so it costs more on the memory allocation. So multi-level paging leads to memory reference overhead. So remember this guys, in terms of main memory, we have certain formula to remember. So physical address is space is equal to the size of the main memory. And your size of main memory is equal to total number of frames multiplied by the page size. So frame size is equal to the page size, no? Since the block must also indicate the frame size and your page size. So if the number of frames in the main memory is equal to 2 to the x, then the number of bits in frame number is equivalent to x bits. No? So, ato ang number of bits in frame will indicate the x bits in the main memory, which is 2 to the x. So, if the page size is equal to the x bytes, then the number of bits in page offset is x bits. So, if we need to represent sample, if we need to represent 8 pages, so we need to have 3 bits. So, 2 to the 3, which is 8, no? 8 pages as we use this formula. So if the size of the main memory is 2 to the x bytes, then the number of bits in physical address is equivalent to x bits. No? Para gyapon dato sa frame if we need to get the frame. So remember also in page table, we have formulas. So number of pages is equivalent to logical address space divided by page size and the number of frames, just physical address over frame size. And the size of the page table is the number of entries in page table times the page table entry size. The number of entries in page table is equivalent to number of pages as the process is divided into. So page table entry size is the number of bits in frame number plus the number of bits used for optional fields, if any. So example, no, in simple basics, like if we have 2 to the 2 power of 2, we have 4, no? Pages. So 2 to the 3, we have 8. So example, if we have 2 to the 10, which is 1024, this can be have a conversion on 1K. If we have 2 to the 20, we have 1M na conversion. And the rest would be 1 giga and 1 tera. So, example, no, mo ni siyang representation ni 16 bits, no? If we have total word nga 8 word, each word of size is 16 bits, no? Each word, each ani will have 16 bits, no? So we can get the capacity memory, which is equal to the number of words in the main memory times the word size. So given here the word size, which is 16-bit, and your number of memory, which is 8 words, no? 8 times 16 bits. So sa 16 bits, ato siyang i-convert because 8 bit, ay, 8 bit is equivalent to 1 byte. So 16 divided by since kuan man siya 16 bits, no, 1 bit, the 8 bits is equivalent to 1 byte. So there will be 2 bytes nga conversion. So we have 8 times 2, which is 16 bytes, no, for this conversion, which is the capacity of our memory. So consider also question here, like consider a system with logical address equal to 27 bits and the physical address requires 21 bits. So the page size is 4K words. Calculate the number of pages and the number of frames. So given here is we have a physical address requires 21 bits. So which is we can convert this one into 2 to the power of 21, and logical address requires 27 bits. So this is equal to 2 to the power of 27. So page size given here is 4K. So we can get 4K, no, like 4K, this can be implied to 2 to the 2 times 2 to the, which is 4 is 2 to the 2, no, 4 times k is implies to 2 to the 10. So we can get the 4K using this one. So by multiplying, we can get the page size of 2 to the 12, no? Multiply. Kung power gani ato yung multiply ay add man nato na siya, no? So 2 to the 12 ang ato ang page size. So the number of pages is given the formula, we have equal to logical address space or divided by page size. So 22 to 27 divided by 2 to the 12, we can get 2 to the 15. And we can get the one its conversion into 2 to the 5 times 2 to the 10, no? Ilan man ang 2 to the 5? We have 32. And 2 to the 10 represents K, no? 32K. So we can get the number of pages into 32K, no? And number of frames, can use the formula like physical address space divided by frame size. Then we can get 2 to the 21 divided by 2 to the 12. And we can get an answer of 2 to the 9, which is 2 to the 9 is represented by conversion 512 na frames. So example, if we have problem number 2, no, consider a system with logical address of 32 bits and physical address space 64 words. So the page size is 4K. Page table entry is 2 bytes. So what is the approximate size of the page table? So as you can see, the given here is the logical address, which is 32 bits. Then the total size of logical address space, if we convert that one, so 2 to the 32. So page size is equal to 4K, which is 4K is 2 to the 2 times 2 to the 10. So we can get page size 2 to the 12. So using the formula, no, number of pages, since they're asking for page size of the table, so number of pages, logical address space divided by page size, we can get 2 to the 32 divided by 2 to the 12, we can get 2 to the 20. So size of the page table in bytes, no, like 2 to the 20, since we have table entry, no, size of 2 bytes. So 2 to the 20 times 2 bytes, we can get 2 megabytes for the page table size, no? So, ingana lang paggamit sa formula. So we can, in terms of address translation, we must consider also the access time, no? Since moagi pa man siya og kanang i-translate pa niya from your paging, no, from pages down to how we can locate that one in a frame, no, in the physical memory. So we must consider also the access time. So one of the implementation here that we in the operating system is using, no, to lessen the access time is the translation loop aside buffer, which is the TLB. No, this is the standard solution to this problem is to use a special small fast lookup hardware cache translation loop side buffer TLB. So this is a hardware implementation used by the operating system, no, to maximize the access time during sa generating the process. So the TLB is associative high-speed memory. It tries to reduce the effective access time. Being a hardware, the access time of TLB is very less as compared to the main memory. So just remember, TLB is equivalent to your cache, no? Your cache is a temporary data registers, no? Wherein katong mga um, usual nga mga data or mga process nga ato ang gina-access. So directly lang to niya ma-access, no? Or we can give it to our main memory, no? For operation. So in terms of hardware implementation with TLB, like we have CPU. So CPU will generate logical address. So it will have page and the offset, no? Sulod ana diha na mo-belong si TLB, which is TLB also have a page number and a frame number, which is diri na nga store tong mga recent processes or data that you're the nga nagamit, no? So sample diri mo sulod una, if natay TLB mo sulod siya una dinhi sa TLB, no? Indicate niya asa nga page number to. So since if nakita niya nga naa siya dinhi imong process or data, so it will indicate na TLB hit, no? Since na nakita man niya sulod ani naa dinhi itong imong gina-access. So it will give a frame, no? A frame number, and also if naay chances nga TLB miss, so wala siya dinhi sa imong TLB nga allocation. So it will go to the page table, no? And will search for that certain frame asa siya na belong, and it will give a frame number and together with the offset, no? Para ma-indicate niya asa specific location yun na belong tong instruction here sa physical memory, no? So consider the TLB like naagit siya operation nga TLB hit and a TLB miss. So important points lang, unlike the page table, there exists only one TLB in the system. So whenever context switch occurs, the entire of TLB is flashed and deleted. So kani ang disadvantages ni TLB. No, once the switching occurs, no, so the data or processes that are recently currently na-store to is ma-delete, no? Once there is context switch occurs, no, ma-delete, mawala na pud to, then katong current na pud nga process ang katong iyang i-remain na pud nga data nga naa to, no? So mag-delete siya from that time nga na mga another process nga execute. So TLB is again updated with the currently running process. So TLB contains only few page table entries, no? Gamay lang siya kay hardware man siya implementation. So few page table entries lang iyang ma-occupy. So if the page number is found, that would be TLB hit, and the pages are allocated to memory. If the page number is not TLB, so it will be TLB miss. So a memory reference to the page table is made. So the percentage of the time that particular page number is found in the table is called hit ratio, no? The particular page number is found in the TLB, no? So it will indicate the hit ratio. So an hit ratio is 80% of the hit ratio, means that we find the desired page number in TLB, no? 80% of the time na nakita nato dato sa TLB na page number. dali ra dito, no? So we can get the 80% hit ratio. And initially, the TLB is empty. So the hit ratio is low, but eventually it increases the process comes. So we can use the formula if we need to get the effective memory access time. So using the hit ratio multiplied by access time for TLB and your access time of the main memory plus your miss ratio multiplied the total access time. So total access time is equal to access time for TLB equal to access time for TLB plus 2 times access time memory. So note that hit ratio is always less than 1. So sample, no, if it takes 20 seconds, nanoseconds to search the TLB and 100 seconds to access the memory, so the map memory access takes 120 nanoseconds when the page number is in TLB. If we fail to find the page that page in TLB, then we access the page table and desired byte in memory total 220 nanoseconds. So what is the effective memory access time with a hit ratio of 80%? So using the formula, no, we can directly plot the um, given values, no, like if we have a hit ratio of 80%, it could be multiplied by 20, no, given the 20 nanoseconds that can TLB will be searched, no, and 100 seconds nga access to the memory. So 20 plus 100 and also the remaining percentage which indicates also the miss ratio which is 20% times the desired byte in the main memory, which is 220 nanoseconds. So, calculating this one, we can get a 140 nanoseconds ng effective memory access time. So, example also, no, like question number 2. So, Q2, consider a system where TLB access time is 60 nanoseconds. What hit ratio is required to reduce the effective memory access time from 300 nanoseconds without the TLB to 250 nanoseconds with TLB? So, find the hit ratio. So, given here the TLB access time, no, which is 60 nanoseconds. So if we have without TLB, we have 30 nanoseconds. Using the formula like 2 multiplied by the access time. So 300 is equal to 2 times access time. So we can get the access time 150 nanoseconds. So for the use of without TLB. So with TLB, so with the use of effective memory access time, with TLB, we can indicate that hit ratio can let be X, no? Since kailangan natin mangita out ka ng value ni hit ratio using the formula. So, from 250 na implementation with TLB, then hit ratio which is X multiplied by the access time to TLB which is 60 nanoseconds plus 150, no, na access time to the memory plus miss ratio can be get from is equal to miss ratio is equal to 1 minus your hit ratio, which is hit ratio is X, no? 1 minus hit ratio. So, hit ratio is X since wa man ta kabalo sa value ni hit ratio multiplied by 60, no? 60 nanosecond total access time plus the 300, no, without the TLB. So, calculating this one, we can get 150x equal to 110. So, x, we can get the x now, no? 110 over divided by 150. So, we can get 0.73. So, we can get the percentage of hit ratio of 73%. So, in terms of memory management, we will have also memory protection. Since in paging, memory protection in paging environment is accomplished by adding an extra bit in page table header. So, by adding that one, we can specify kung kani siya nga certain process is protected, no? By adding a bit. So if it's set to 1, that means the page is read only. So if set to 0, then it means it can be modified. So one additional bit is generally attached to each entry in a page table, which is a valid or invalid bit. So by this, any illegal attempts will be trapped to OS. So example, no, from this given pages 0 to 5, and it indicates here from 0 to, from that page table, no, like 0 to 7, ana siya. So naa siya um certain pod nga mga frame number nga indicated in a physical memory, no? 0 is 2, 1 is 3, 2 is 4, 3 is 7, 4 is 8, 5 is 9, 6 is 0 since walay sulod, no? 6 ana siya. So empty siya. 6, 7, since wala man siya, tama naman siya sa page 5. So 6, 7 is wala siya. Empty. No? Since makita na to din sa physical memory, like 0 and 2 is sa frame 2, like naa siya naka-point na page 0. So this is a valid bit. No? So mo ni siya ang protection nga side. 9 also is indicated with page 5. So page 6, 7, since wala man siya ga-exist, it is empty. So it is invalid bit. So valid, it can be read, no? Invalid would be, can be modified. So shared pages. So an advantage of paging is the possibility of sharing common code. So if the code is reentrant code, it can be shared. So reentrant code is non-stop modifying code. It never changes during the execution. So thus, two or more processes can execute at the same code, using the same code. So therefore, many of the heavy programs such as compilers, your run libraries, or database systems can be shared, no? Using the shared pages. So example, no, like page 1, naa siya'y 1, 2, 3 nga pages. And naa siya'y data, no, nga ginahold, data 1. And same with page 2. We have 1, 2, 3 nga pages. So naa siya'y data 2 nga ginahold. So same as P3, no? Every process na siya page table na gina-create. So we have page table 1. So page table 1 is in 3, no? Frame 3. So kana siya. 4, 6. So your data 1 is in a frame 1. So mo na siya. So are they sharing the same code, no? 3, 4, 6, naglahi lang dayon siya sa iyahang data kung asa na build. So to lessen the allocation. So we have also the structural of page table. We have hierarchical paging, hierarchical page table, and inverted page table. So we have also a multi-level paging. So the larger page table is not desired because they can take a lot of memory. So how we can reduce the page table size? Solution 1 is to use the increasing the page size. But then this infers to internal fragmentation na mahitabo if we use the increase of page size. So we can use the multi-level paging. So say nasa multi-level paging algorithm. So it is a paging scheme which consists of 2 or more level of pages in hierarchical manner. It also known as hierarchical paging. So it is needed because sometimes situation arises that the page table itself becomes large. So therefore, we cannot keep the page table in memory contiguously. So therefore, the solution is to divide the page table in two smaller pieces. So naaram din mo occur nga two-level paging. So that is a page table can have itself a page, no? Naa siya, page table will have another page on itself. So using the illustration, no, yapon. So as you can see, here we have outer page. We have an outer page. So outer page table, no, sulod ana kay napod siya page table, no, na naka-indicate. So several kuan niya no into a smaller um a page table can have another page, no. So from that also in a memory, certain pages will point to some ranges of this one, like page kana siya, di na siya naka-indicate sa frame 1 to 500. So, i-divide into in smaller pieces. Page can have a page in itself. Now, as you can see also here, logical address, no? Like P1, page 1. Kana sa page 1 is the outer page table and it will pointed in page 2 also, no? And using the offset, we can get the certain instruction, no? If ato na siyang i-locate dito. So hash page table, this is a common approach for handling address space larger than 32 bits, is to use a hash page table with the hash value being the virtual page table. So each element consists of three fields, the virtual page number and the value of map page frame, a pointer to the next element in the linked list. So sample, no, if a logical address will generate this one, page and offset, so it will go to the hash function and will give an entry, no, will give from this hash function it will generate from to locate kung asa dapit siya nga hash table, no, and from that i-check din to niya from the hash table, it will check from the linked list, no, sample P1 will have a frame 3, no, since then wala pa man, since ang page 3 man siya din so it will check another link again, link sa linked list. So makita niya diri page 3 will have a frame 5. So it will match from the logical address nga generated from the linked list, no, page 3 and page 3. So it will indicate a frame 5. So nagmatch, nakita niya nga frame 5 to siya. So it will add up to the offset. So makita na din niya din sa physical memory nga na siya sa frame 5 kaning page 3, no? Since hash table is using a linked list. So inverted paging, to maintain a page table of all process will consume a huge amount of memory. Therefore, it is said to maintain one page table for all process. So an inverted page table has one entry for each real page memory. Each inverted page table is a pair. We have a process ID. No, page table will have a process ID and page number as indicated for inverted paging. So where the process ID assumes the rule of the address space identifier. So example, if the CPU generate a logical address, so it will give a process ID and identification as well as a page number, no? So, iyang i-search taman kung asa naka-point, kung asa ra gyud nga unique process identification of this certain page, no, after that searching it will indicate an I, no, which is the number of, it will be used as a number of frames nga imong indicate dadto pagbalik dadto sa paglocate sa frame number. So I would be a frame number together with the offset to get the specific location or kaning sa instruction diri sa physical memory, no? With the use of process identification, page identification, or process identification, i-search niya from time to time, siya makita din niya nga naa siya diri, no? Kaning process identification na belong siya din with that certain page. So i-upon nito niya from the travel, no? And it will indicate the number of frames. Together with the offset, we can get the physical address, no, from this physical memory. So we also have a segmentation, which is another part of the non-contiguous allocation, memory allocation. So What is segmentation? So part of the paging, we must know first the what the user's perspective, no, in terms of how paging works. So paging does not preserve users' view of memory allocation because as the physical location of the page may change at its swap in and swap out of memory when we are using a paging technique. So any assumptions made by the users about the physical location of a certain page, it would be incorrect because of the swap in and swap out implementation ni paging, no? So na dynamic allocation, dynamic location in terms of these certain programs or data. So, as you can see, in ani iyahang figure in terms of how the user would see, no, in terms of our main program, shared libraries or stack or anything ng mga functions that you are implementing in your program, yung ani ang makita sa users. Pero this is not good in terms of the paging. So what happened, no, if we have our main program, shared libraries and stack, so each portion of the program is divided into equal size pages and stored in the physical memory frames, as you can see here in the physical memory. So main programs would be in different locations, no, of your physical memory as well as your shared libraries and stacks. So what does it mean in terms sa segmentation? No, as you can see, if the user's perspective, ang ato ang expectation is that the main program, shared libraries and stock are at the same location. No, user thinks all these program segments are at the same place, but this not applies to paging because of the different allocation in terms of um, implementation of swap in and swap out, no, during the process. So what is segmentation? Segmentation is a memory management technique in which memory is divided into variable size chunks which can be allocated to processes. So each chunk is called segment, no? A block can be called as segment of each of the program. So a table stores in information about all such segments called the segment table. So in terms of paging, we have a page table to map out our logical address to memory address. But then in terms of segmentation, we have a segment table for the mapping. And segmentation is a memory management scheme that support users' view of memory. Why? Because segmentation preserves a user's view of memory by dividing logical memory into a variable size chunks, which is segments that corresponds to different parts of your program. This could be part of the code segment, data segment, and your stack segment. So it has a unique name, a logical address space, and the location of each segment is fixed and does not change during program execution. So this preserves that the user's view of memory and allows programmer to reference specific parts of the program with ease. No, sample, if we have an example here for illustrating the segmentation, no, like sample, we have main program, shared libraries, and stack in your logical memory. So there are several instruction inside of it, no, like your main program, it has four line of codes and processes, and we have also your physical memory. So in the physical memory, your main program is allocated in um, here to 0 to 4, and the other would be 14 to 17 and 18 to 23. So what segmentation works on that, like main program, shared libraries, and stack can be segmented, no, into different, no, like we have segment number 1, which is main program. This allocated for main program, and segment number 2 would be shared libraries, and stack number 3 that would segment number 3 that would be a stack, no, for allocation. So based on the segmentation, we must also to consider the base, no, location of this certain segments and its length. So in terms of segment number 1, which is the main program, in the physical memory, we can see that one have a fixed range from 0 to 4. Why 4? Because the length given is 5. So we must count till allocation number 5. No? So 0, 1, 2, 3, 4, and that compromises for the length of this main program. So the stack would be 14 to 17, no? Because of the length from 4, and the base is 14, and the shared libraries would be the base is 18 and goes to 23 because of the length 4. So as you can see here in segmentation, we have segment table. So this maps out our logical address to memory address. So we can have a format like 1, 3 that indicates a segment number, no, which is 1, segment number 1, and the offset. Kung asa nga specific nga instruction ang atong pangitaon dito sa physical memory. So example, if we have a main program which is segment number 1, so we're locating the main program segment number 1 and the offset which is 3. So instruction 3 from in the main program. So pangitaon nato siya din sa physical memory as well. So what we do is the fetch the base address, no, since fetch the base address. So the base address of main program segment number 1 is base 0. So check the offset between 0 to length. So we have a length 5. So we for the segment number 1, we have 0 to 4 nga allocation. So we must add the base and the offset, no? If step 2 does not have any error. So atong buhaton, get the base of segment number 1, which is 0, plus the offset, which is the instruction 3 that we need to locate in the physical memory. So 3, no? 0 plus 3, we can get a 3. So here we can locate that physical memory na belong siya sa 3 nga frame. So ing ana ang pamaagi ni segmentation. So the advantages and disadvantages of segmentation. So in terms of advantages, we have segmentation eliminates internal fragmentation, so allows dynamic segment growth, and it is visible and assess dynamic linking. So as well as the programmer have the reference, no, in terms of how they will see the location of the certain instructions that was a physical memory. So disadvantages, we have maximum size of the segment is limited due to the size of the memory and difficulty managing variable size segments on the disk storage. Since fixed man siya, no, so kinahanglan nato siya, we have more memory size, no, ato i-upgrade to memory size in terms of the segmentation. So sample problem, no, like on a system using simple segmentation, compute the physical address for each of the logical address is given in the following segment table. So if the address generates a segment fault, indicates. So you can see na ay different kind of segmentation na gihatag, like A 0 to 0 and 99, B 278, C 1 256, and D is 3 222. So as you can see, we have generated a segment table, no, from 0, 1, 2, 3. These are the base and length respectively. So sample, if we go to question letter A, no, we have 0 and 99. So segment is equal to 0 and the length would be, since 0 man na, so 0 atong segment. Then based on the segment table, ang length kay 124. So the offset should be between 0 to 24. It tells that the offset is 99. So ang range is 0 to 124. That is okay, no, in terms of addressing, no, physical address. So base plus the offset, no, 300 from segment table, we have segment 0, which is base is 330 plus your offset, which is 99. So your physical address would be 429. Ito na mo na malocate ang imong instruction sa physical memory. So in terms of letter B, we have 278. So segment number 2, we go to segment number 2 and the length is 99, no? So offset should be between 0 to 99. So 78 is okay. Nasulot siya ng arrange. So we can get the physical address with the formula base plus the offset. So based on the table, we have 111 nga base plus your offset, which is 78. So we have 189 nga physical address. So as well as letter C, no 1, then 256. So segment number of and your offset. So segment number 1, yung point and length of segment number 1 is 211, no? So as you can see, ang ato da pang offset kay mabilong siya sa 0 to 211, which is your offset nga gi-declare is 256. So lapas na siya. So it's not okay. So a segmentation fault occurs in this part of the processes. So we jump to we cannot get the physical address of this one because naa na siya error nga mag-occur. So 3 to add na to sa letter D, which is 3 and 222. So segment number 3, which is the length is 302. So we can get the range from 0 to 200, 302. So 222 is okay. So physical address, we have 498 plus 222, which is 720 nung location in our physical memory. So that's how you get the physical address in terms of segmentation. So paging versus segmentation, we have paging. Now paging suffers from internal fragmentation. So paging does not preserve user's view of memory allocation since it is dynamic. There is no external fragmentation. Unlike with the segmentation, there is no internal fragmentation. Segmentation is visible to the programmer and there is external fragmentation. So makita ninyo nga naagi siya opposite nga side, no? It's like si paging kay internal fragmentation kay problem niya, but then sa segmentation kay dili niya problem ang internal fragmentation. The segmentation kay makita niya ang memory allocation, but then in terms of paging dili niya makita in terms sa programmer. So if sa external fragmentation kay si paging kay wala problema, but then segmentation na siya problema kang external fragmentation. So ingana ang nitabo, no? So naa siya mga disadvantages and disadvantages. So what we do from disadvantages and disadvantages, we have page segmentation nga solution. So it is thought to utilize the advantages of paging and segmentation. So we combine the two implementation because of the user space is broken into number of segments and each segment is turned broken into fixed size pages. So from the user point of view, the address would be segment number plus the offset. But then the programmer point of view, the address would be segment number plus your page number and the page offset. So in terms of page segmentation, we can see this one in the figure, no example. Like our main program, it has segmented, no? Pila siya nga blocks ang nasulod ana. So shared libraries also as well as the stack and your functions. So the program is divided into segments. It preserves the user view of the program and the segments are further divided into pages, no? Isapaw na to ang segments, napagid siya pages sulod. So the non-contiguous memory allocation can be implemented effectively. So page size must be equivalent to frame size, which is your physical memory. So this is how we how this page segmentation allocation. So as you can see, different segments, different sulod po sa segments, we have pages. So this is allocated in specific physical memory at locations. Diha yung mga range. So naka-point lang na siya, no, dito sa itong physical memory. So our main program, naapod siya mga segments, naka-connect po na siya dito sa physical memory. So nga na gabuhatan ni page segmentation. So important points, pages are smaller than segments. So mas dako si segments, no? Each segment has a page table, which means evenly programmed has multiple page tables. So imuhang segment na inay mga page table pod nga kapare. So suppose we have 5 segments in a program, and there will be 5 page table ang atong buhaton. So here two tables are used, segment table and page table. So segment table contains the information about every segment. So each segment table entry points to a page table entry. So important points also, logical address is equal to your segment number and the offset. So segment number is used to index segment table. So each segment table entry consists of segment length, then the page table base. And the logical address is valid if the offset is less than the segment length. Logical address is valid, no? If na mahitabo, we have segmentation fault. So the segment offset is divided into two parts. We have page number and your page offset. So here, page number is used to index the page table of the segment. So page number is used to index the page table of the segment. So here, makita na tong illustration sa page segmentation. So a CPU will generate a logical address. So together of that logical address, we have generated a segment number and a page number and your offset. So what we do, we add up the output of SBTR plus your segment number and locate that one in the segment table. So makita na dito sa segment table nga naa dito ang kaning segment number nga imong ipangita, no? So it will undergo also to add up the page number and your segment number nga gipangayo dito sa segment table. So ato na siyang i-add, then we can proceed to the page table and locate that one kung asa nga frame siya na belong, no, dito sa page table. As you can see, a segment table must have a page table, no, para ma-locate na to tong frame. So if there is a match nga occur from this, then we can get the frame number and we'll add the offset. So we can get the frame number and offset, then we can get the physical address and we can locate that data here, no, kani nga all nga locations from our main memory. So ingana siya mag-translate si page segmentation. We have undergo siya una with the segment table, segmentation, then then ang paging. So advantages, it reduces memory usage, it simplifies memory allocation, and page table size is limited by the segment size. The segment table has only one entry corresponding to one actual segment and no external fragmentation occurs, and each segment could be set up as an access right. So we also have in memory management a virtual memory. No, this is a separation of user logical memory and from your physical memory. So only part of the program needs to be in a memory for execution. Ato ra mga certain or mga part of your program nga kanang main na ginagamit that could be stored for the execution lang. So logical address space can therefore be much larger than your physical address space and allows address space to be shared by several processes and allows for more efficient process creation. Munang na-create na to ang virtual memory. So what virtual memory does, so it gives an illusion to the programmer that a huge amount of memory is available for waiting and executing the programs greater than the size of the physical address space. So you have your physical address, then if kulangon na ay virtual memory nga mo assess ana in terms of how we can process that certain data if kulang na gid ang physical memory, no. So na ay virtual memory nga concept. So as you can see here, without the virtual memory, logical address is equivalent to your RAM address. So this is very limited. So sample, if we have a logical address from 0 to 5, and it can be allocated from our RAM address, which is 3 ra 0 to 2, Then katurang mga 0 to 2 nga process ra iyang ma-allocate ani nga kuan to execute its program. In terms of 3 to 5 wala na. No kay ano man limited lang man ang iyahang memory because this walay part si virtual memory dani. So what we do if we add up a virtual memory, so logical address will map to RAM address, no, i-map niya kung asa man ni siya pwede. Kung say free nga RAM address, dito siya mosulod. So sample, if we have 0 to 5 nga logical address, so as you can see, 0 is pointing to RAM address 1. Logical address 1 is pointing to RAM address 2, as well as 2 is pointing to RAM address 0. So, na-allocate na tanan, wala na isulod, no? Dili na magamit ang RAM address. So, what we do, we'll map out to another storage, which is our virtual memory. Ito na siya mosulod. So, sample, F3 will execute its program, i-map out siya, isulod siya dito sa ato ang another storage, which is our virtual memory, to execute its program. So, ingana ang purpose ni virtual memory. So, sa virtual memory also, we have pages, no, in our virtual memory. And we can memory map that one in our main memory. So, paingon dayon sa imong physical memory. And using the backing storage, dito na to makita ang certain sulod na to atong data dadto, then it will transfer again to physical memory for for processing the data. So advantages of virtual memory. So system libraries can be shared. So you can see now, like we have kaning certain pages kay will access to the same library. No, if ever the other program also need some part of the library, so you can share that one. So virtual memory enables process to shared memory. So virtual memory can allow pages to be shared during process creation with fork system function call, thus speeding up the process creation. So implementation of virtual memory, we have demand paging and demand segmentation. So in terms of demand paging, it allows the pages that are being referenced actively to be stored in the memory. So it allows bigger virtual address space and provides the illusion of infinite physical memory. No, it allows infinite memory. So naana siya technique later on. No? It allows more process to fit in the physical memory and to be running at the same time. So bring a page into the memory only when it is needed. So it occurs that less I/O needed, then less memory speed, and faster response and more users. So what demand paging do is from 0 to 5 nga dili sa ato ang page, no, we have page 0 from page 3. So page 0, 1, 1 and 2 is allocated dito sa RAM. So na sila'y kuan location dito sa RAM. So we have 0, 1 to 2. Pero pag mosulod na si 3, moagi siya og i-map out siya paingon dito sa ato ang virtual memory. So ang mahitabo katong mga daan sa demand paging, katong oldest nga page nga na-accommodate could be page out, no, and store to remove the page 0, which is the oldest page, and bring P3 in the memory for execution. So nahitabo P0 is gipagawa siya, and that would be called page out. So mahitabo dayon to execute the P3, we need to allocate that one in the RAM, no, kung asa na free after nga mag-page out. So nitabo P3 will execute na its process, no, wala na siya sa ato ang virtual memory. So nag-demand man siya, Nga kailangan ako na pod. So, kailangan siya gawas ng P0. So, P0 is naman siya sa the other storage. So, kailangan ibalik na po siya dito sa virtual memory nato. So, we can, and that process would be called page in, no? So, that page P0 would be used for other time if kinahanglan na siya gamiton, no? So, naka-point out na po na siya dito sa ayan P0 is naka-map na siya dito sa virtual memory. Unlike atong ganina, no? Si page 3 kina sa virtual memory but then ma-change na dayon iyahang map. P3 is na siya sa RAM address 1 and P0 na siya sa ato ang virtual memory. So types of demand paging, we have demand paging, pure demand paging, which is all empty frames are to be considered, no? Kung free nga frame, pwede ko dato isulod. So mag-demand ko nung ako una. So we also have prefetch. So before execution, they are loaded, no? So kibali na sila pre-assessment, pre-process pang mahitabo before sila full execution. So niagi na sila og sa RAM na ano, niagi na sila but then wala pa sila fully na process. So in terms of demand paging, we have a software implementation with the use of lazy swapper, which is never swaps a page into memory unless page will be needed. So swapper that deals with a page is a pager. So you can see our program from program A from the main memory will be swapped out and put back to our backing storage and we'll get the new process and to be swapped into our main memory for our execution. So we also have a valid and invalid bit, no? Same as sa page table to indicate with each page table entry a valid invalid bit. So valid in memory, V ang iyahang implementation and I would be not in the main memory. So initially valid and invalid bit is a set to I on all entries. So during address translation, a valid and invalid bit is in page table entry. So it will indicate no kung naabagit siya sa main memory nato. So it will be a valid or invalid. So page fault occurs when we access a page marked invalid and it causes a page fault. So a reference to the invalid page will cause the hardware to trap and the operating system performs a series of steps to handle the page table. So this means nga it is basically if a memory error and it occurs when the current programs attempt to access the memory page for mapping into virtual address space, but it is unable to load into the physical memory, then it is referred to as page fault, no? Like, na-invalid nga mo occur dito sa imo ang page table, no? Makita nimo dayon pag-load dito sa virtual memory, wala dahil siya. So, unang page fault nga mahitabo. So, if we have some illustration, no, as you can see, if we load this one, load M, and we get the references from the page table. So, what do? Kung invalid, itrap niya. So, it will get a system error and operating system will page pages no dito sa backing store. So dito niya allocate and bring the missing page back again to the free frame and dito niya ibutang sa atong physical memory and it will reset the page table since dili naman siya invalid, no? So na siya free frame and it will restart the whole instruction so that again it will occur to execute the instruction. So what happens if there is no frame? So page replacement find some pages in memory but not really in use, so swap it out. So same pages may be brought into several times. So in terms of page replacement, you can use that one. No, if the process happens in computer memory management. So when computer is running a lot of programs at the same time, it need to use memory efficiently to keep everything running smoothly. But one way to do this is the use of this paging, which is breaks the computer memory into smaller chunk called pages. However, when there are more program running than there are pages available, no, daghang kay program din, gamay ra imong pages na available. So, the computer needs to decide which pages to keep in the memory and back to the backing store and have a free space to swap out to the hardware, and this is called page replacement. So, the computer uses algorithm to determine which pages to swap out based on the factors like how often they are used or how important they are to the program. So nga na ang gabuhaton ni page replacement, no? So sample, basic page replacement. First step, we need to find the location and the desired page on the disk and find a free frame. If there is a free frame, we use it, and there is no free frame, use a page replacement algorithm to select a victim frame and bring the desired page into the newly free frame and update the page and frame tables and restart the process. So this is how the basic page replacement works. So sample, if we have a page table, no, then the page table will indicate a frame and a valid or invalid bit. Example, we have 0, which is it states that invalid, and F, we have, in our frame, we have F, which is valid. So first thing to do is we need to seek a victim frame. So that victim page will be swapped out in our backing storage, and it will be indicated that our invalid now would be and this part din sa atong page table like kani siya, no, this would be changed into invalid. So mahitabo swap desired. Ang next ayang button is swap desired page in, no, if our newly free frame, which is this one, and we'll update the table since then ato naman siya gi-change into invalid, no, update na to ang ato ang page table so that lahi na po ito yung i-point, no, for the invalid. So nga na ang page replacement nagakahitabo. So we need to restart from time to time the page table, no, if we swap in and swap out our paging. So I think that would be all for the memory management. Thank you very much for listening and good luck.